Welcome back. In the second part of this section, we're going to look at differentials. So again, starting with the beginning of us having a tangent line drawn at some point C, if we're thinking about the change that we have, there's a change in x and a change in y for both the tangent line and also both the curve. So we're starting off with dx and delta x. Both of those are going to represent the change in x, because whether we're thinking about going from c to x on the tangent line or going from c to x on the curve, either way, it's a change that's the same amount. So dx and delta x, that's identical amount for both. The change, whether we're changing x for the curve or changing in the x direction for the straight line. Now, for the y direction, there are two different values. We have dy, that's the change in the y for the tangent line, and delta y, that's the change in the y for the function. And those two things are not the same as each other. But same sort of thing as we noticed at the beginning, though. If you're close to c, then delta y and dy will be relatively close. So further away, delta y might be quite a bit bigger or quite a bit smaller than dy, but if we're really close to c, then delta y and dy will be almost the same. So something that's true, and is this little relation that we have here, that dy is f prime of x dx. And the reason for that is f prime of x, this is the slope, right? And the slope, of course, is the change in y divided by the change in x. And we're multiplying it by dx, and dx is the change in x. And of course, the change in x cancels, meaning what you're left with, which is just the change in y. And that's exactly what dy is. dy is the change in y for our tangent line when we have a change in x dx on our tangent line. So we're going to use this as a way of doing an approximation now. We can say, well, if we're interested in approximating how much of a change we've got in the y values, I can say, well, the change in the y value on my tangent line should be approximately the same as the change in the y value on my function. And since I can easily calculate the change in the y on my tangent line, I can use that to approximate the change in the change in the y value for my function. Okay, so I've got this function and I want to use differentials to figure out what is the approximate change in this function. So for this one, I'm going to have to be careful because when I'm thinking about dx, the change in the x values, I'll have to think about what kind of change is it? Is it an increasing? Is it a decreasing kind of a change? So for the first one, if I'm looking at x increasing from 1 to 1.1, then my change in x, my dx, would be something positive. Remember that, of course, a change that's positive would be a positive change, an increase. A change that's negative would be a decrease. So since we're going from 1 to 1.1, we have increased by 0.1. So my change, my dx, or my delta x for that matter, those are both 0.1. If I'm looking at now what is f prime, because remember, of course, my formula said that dy is f prime of x times dx, and we're using this to approximate the change in y, so delta y is approximately f prime of x times dx. So I guess I need to figure out what f prime of x is, and I'll do that up top. 3x squared plus 6x minus 2. And we're approximating this at x is equal to 1. So we're starting at 1 and then ending up at 1.1. So when I figure out what is f prime, it's really what is f prime of 1. And that would be 3 plus 6 minus 2, which is 7. So now I'm good to go. I can say to myself, well, I said that delta y would be approximately f prime of 1 times dx, and that is 7 times 0.1, which is 0.7. That's my estimated change. If I wanted to find out the exact change, so maybe we'll do that down below. We want to find the change in the y values as we go from 1 to 1.1. So if I wanted to know the exact change in y value, that would be ending at 1.1, starting at 1. So I would look at f of 1.1 minus f of 1. So if I put 1.1 into my original function, I get 3.761. And when I put 1 into my original function, I get 3. So the actual change in y value is 0.761. So the estimated change was 0.7. Our y values go up by 0.7, is actually really close to the true value, 0.761. And the reason why it's not surprising that the two values are close to each other is because the distance between the two is relatively small. That 1 and 1.1 are relatively close to each other, so dy and delta y should be relatively close to each other. So now looking at this one, I'm going to imagine that this one's going to have less of a closeness to it because we have a bigger gap. We're going from 2 to 1.1. So for this one, if I were thinking about what is my dx or what is my delta x, it would be something negative because we're decreasing. We're going down by 0.9. So my dx, or my change in x, is negative 0.9. Again, if I were doing the same business as before and figuring out what is f prime of 2, since we're starting at 2, I'd find out that that's 22. And so delta y, which is approximately f prime of 2 times dx, which is 22 times negative 0.9, or negative 19.8. This is our estimated change in the y values. If I wanted to know what is the actual change, so if I wanted to know actually what is delta y, well, this is, of course, starting at 2, ending at 1.1, so going to 1.1 from 2, we need to calculate the end minus the start, so f of 1.1 minus f of 2, so 3.761, and when I put 2 back in my original function, I get 17, so I get an actual change of negative 13.239. So there's quite a big difference. I dropped my negative, shame on me. There's quite a big difference between the two. So they're both correct and showing that there's a decrease in the y values, that as our x values decrease from 2 to 1.1, we estimated that our y values would go down by almost 20, but actually, in reality, our y values only go down by about 13 and a little bit. And the reason for the delta y and the dy not being as close to each other as we'd like is because we have a bigger gap between the 2 and the 1.1. The previous part, we had the 2 points were really close to each other. They were only 0.1 apart from each other. Here the points are 0.9 apart from each other. It's a bigger gap, which means a bigger difference between dy and delta y. Okay, so of course, in any sort of computation that we do in our lives, any sort of measurement that we do, there's always going to be error built in, measurement error. So we have measured something C, and the actual quantity is really C plus our little error amount, our delta X. But of course, you used that value C to compute other things. So for example, you measure the radius of a circle and you're using that radius to calculate the area or calculate the circumference. If your radius is wrong, then the area will be wrong too. And of course, how the area, how the radius got used in the area formula will have an impact on how much of an error you'd have in your area calculation. Or if we were measuring a sphere and I measured the radius incorrectly, then the volume, for example, there would be an error in my volume measurement if I used an incorrect radius measurement to find that. So this is what we want to find out. What is the propagated error when we use one measurement with an error in it to calculate something else? How much of an error do we get in the something else? So if we use C to compute a value, then how much of a difference we'd get between the actual value and the value we calculated, that is the propagated error, delta y. So delta y, this is again just the change in the y values. This isn't anything that's really new, really. If you're thinking about what we're talking about, we haven't done anything other than really rephrase what we had in the original diagram. So when we say delta y, it is just the difference between the two y values, the y value at c and the y value at c plus delta x. So the nice part, of course, is that if you wanted to estimate things, although you could find the exact error, you could estimate the error just by using the differential. You could say, well, we know that dy and delta y are relatively close to each other, so we can estimate by using dy is f prime of c times dx. If you wanted to know what is the relative error, how much of an error do you have compared with the actual measured value, that is the relative error. So here we're comparing, or we're scaling things in terms of how big is the actual y measurement itself. So our delta y divided by y, that's our relative error. And if we wanted to turn that into a percentage, then multiply by 100 to now turn it into a percentage. Of course, just as before, we're going to use dy as an approximation for delta y. So if you wanted to actually calculate the relative error, you'd calculate delta y over y. But if you just wanted to approximate it, you'd calculate dy over y, or the percent error with 100 times dy over y. Okay, so let's do this little calculation. I've got myself a cube, so of course we know for a cube the side lengths are all the same, and we've got a volume that's just x times x times x. Or in other words, x cubed. So if you make a mistake measuring the side length of this cube, then that's going to, of course, have an impact on the calculation you get for volume. So I've done my measurement. It's 30.2 centimeters. But I know that there might be an error on either side, plus or minus 0.1 of a centimeter. My little measuring tool only has that kind of precision. It can only be good to within 0.1 centimeters. So the actual side length might be as small as 30.1, or it might be as big as 30.3. That's the best I can do with what I've got. So let's figure out what we've got here. We know that if we're looking for the change in the volume is about the same thing as dV. And I know if I wanted to find dV, that would be v prime of x times dx. Of course, if my volume is x cubed, then v prime would be 3x squared. So now I just want to figure out what is the change that I'd have in my volume with that little 0.1 of a discrepancy. How much of a change would that make to the volume? So putting in what I have, if I had 30.2 for my x value and dx was 0.1 because I'm close to plus or minus 0.1, I would get 273.612 centimeters cubed. So in other words, if my side length is off by up to 0.1 centimeters, then my volume will be incorrect to as much as 273-ish cubic centimeters off. If I felt like it, just as a little side if I wanted to see what is the actual error, so actually what would be the error possible, I might say, well, I could have the actual y value be as big as, have the actual side length be as big as 30.3 when the volume that when the side length I calculated was 30.2. So in other words, I could have the actual error be 30.3 cubed minus 30.2 cubed, or 274.519 centimeters cubed. Or on the smaller side of things, what if my 30.2 was too big? I could have an error 30.2 cubed minus 30.1 cubed. My actual error could be negative 272.707. So I could be overestimating things or underestimating things by about 270-ish cubic centimeters, which is very close to what I found with my approximation, 273.612. So that's how much my error might be off. I might be over or underestimating the volume of that cube by as much as 273 cubic centimeters. So what does that mean in terms of relative area? So here we want to compare that relative error or the error that we have to the actual y value. I know that I have that the relative error should be delta y over y, but we're going to approximate that with dy over y. dy we just found. That was in this case, instead of y's, I should say v's, because our function is a volume function. We already calculated out what dv is, so that was easy enough for us to do. We just need to find out what v is. dv, that was the 273.612. And v, this is our actual calculation that we get with our 30.2 cubed for the volume. And when I do that, I can see that it's actually not a big discrepancy actually at all, because the relative error is 0.00993377 and a bunch of other stuff. The 273 cubic centimeters sounds like a lot, but if you find out what the actual volume is, the actual volume that we're calculating is in the nature of tens of thousands of cubic centimeters. The actual volume that we calculate is 27,543.608. So although it sounds like being off by 273 is a lot, compared to the actual volume, it really isn't that much, and that's why our relative error is a small amount. Probably even easier to understand it as a percentage. How much are we off as a percentage in our volume calculation? That would be 100 times our previous number, which is 0.993377 approximately, or in other words, less than 1%. We're almost 1% off in our volume calculation, which in the grand scheme of things is not a whole lot. So delta V over V times 100 is just a pinch under 1, so how much our volume measurement is off? Just a little bit by 1%. Okay, so one last little thing to do here is to approximate values with differentials. And again, using that whole idea again of dy and delta y being close to each other. So if I wanted to find out what is the new y value on my curve, I could do that by taking my original y value and adding on delta y. But if I wanted to do an approximation, I could say, well, instead of doing that, I could take my original y value and add on dy instead. And if dy is close enough to delta y, then the y value I get should be relatively close. So that's sort of the idea here, that if you wanted to find the y value on your curve, take the original y value at your starter point and add on how much of a change in y you have. And of course, we use the fact that dy, our differential, is f prime times dx. So that gives us this formula here, that if we're looking for an approximation at c plus delta x, so if we wanted to find out what is this approximate y value, we take the y value where we start, plus our slope at c, times our change in our x value. In other words, we get our change in our y value that's on our tangent line and add that on to our original y value, and that gets us something that's close to the true y value. So I'm going to use this to calculate cube root of 30, this idea. So I'm going to, of course, start with a function, and my function is going to be the cube rooting function. X to the 1/3. And so if you did the derivative of that, you'd have 1/3 x to the negative 2/3, or if you were to rewrite that, 1/3 x to the negative 2/3 is 1/3 x to the 2/3 with a positive power now. So if I'm looking for f of c plus delta x, we said that that's approximately f of c plus f prime of c times dx. So here I need to think about where is my c, where am I going to start at, and then how much of a change, how much is dx. So I think about what can I find the cube root of, and I know cube root of 27 is 3. That's an easy one for me to calculate. So I'm thinking about c, my starting value as being 27. And to get to 30, you would have to increase by 3. So in other words, dx would have to be 3. So picking 27 as my starting point means dx is 3. Another option you could choose, which I think is a worse option, but you could choose 64. You could say, well, I know cube root of 64 is 4. But if you started with c being 64, then dx would be a lot bigger. In fact, it would be negative 34, because to get from 64 to 30, you'd have to go down by 34. So this is where we have to be cautious and ask ourselves, from our starting value, am I increasing or am I decreasing, and by how much? That's our dx. So away we go. If I want my cube root of 27 plus 3, or in other words, if I want my cube root of 30, I will take f of c, cube root of 27, plus f prime of c, 1/3 times 27 to the 2/3, times dx, which is 3. So that cleans up not too terribly for me. So if I did that, cube root of 27, that is 3. 27 to the 2/3 is 9. 9 times 3 is 27. So for my fraction, I'd have 3/27, or same thing as 1/9. As a decimal, you get 3.11111, and so on. And if you were looking to compare that with the actual value, it's not too far off. Cube root of 30 is 3.107 and some other stuff. And so actually relatively close to what we found with our approximation. And again, the reason why it's close is because we were approximating with not a very big change in x. That if our x values aren't changing that much, then the y value we find on our tangent line and the y value we find on our curve are approximately the same.